Can you see my slides?
Yes, we do.
Okay. So thank you for everybody for being here. I will, just like Matei said, I will present on the performance, portability, and scalability of codes using Kokkos and all. We are going back for a more technical presentation now. And just as a motivation, the HPC landscape nowadays is very heterogeneous and very large. By heterogeneous, we mean that in the top 10 or the top 8 supercomputers here, we have examples using accelerators from AMD, NVIDIA, and Intel. Within the systems that we have here in Europe, we have AMD and NVIDIA systems on the top 10 from the top 500 supercomputers. The Jupyter supercomputer will be coming soon, and it is an NVIDIA system. And with this, there is a high necessity of maintaining a lot of code, or at least maintaining code that can compile for different architectures. Within the Gauss supercomputing centers, we also have an example of a system that has Intel accelerators, and this is a major problem for most of the scientific codes. If one wants to have portability, it is necessary to be able to compile your code for all of the major vendor architectures. And another problem also rises with the systems being very, very large. Which is the case for exascale supercomputers. Naturally, there are loading balances, so one processor can be slowing down your whole simulation. Scalability and parallelism is definitely a challenge that occurs with a high number of nodes. The heterogeneity of architectures as well, because we have this very fast accelerators, the GPUs, but the CPUs themselves are really good nowadays. So one wants to use both architectures to its best potential, and therefore using all the energy of the system efficiently. And to tackle this, on the intranode side, there are different programming models that can help us to port our code, or so that we can program our code that in a manner that runs for different architectures. Speaking a little bit about the solutions, we'll focus this presentation now on Kokkos, but this is just a slide of the many different programming models that one could use to program either native solutions for each one of the architectures, for example, CUDA for NVIDIA, HIP for AMD, and SYCL for Intel GPUs, but also perform portability programming models such as Kokkos, OpenP, Aja, Alpaca, OpenSC, and so on. So here we'll be focused on Kokkos, just to give you a little bit of history about Kokkos. It has been developed for more than 10 years. Its first use in LAMMPS was in 2013. The development has gone forward, and between 2015 and 2018, the support for many different architectures was developed. So this was major the development of both the NVIDIA backends and the AMD backends. Nowadays, it has a backend for SYCL as well as different vendors, different CPU architectures. And nowadays, it has been used in the biggest machines in the world. But one very important topic about performance portability and the sustainability of scientific codes is the future. And so how future-proof our solution it is really. And a little bit earlier this year, Kokkos began to be part of the High Performance Software Foundation, which is an umbrella organization from the Linux Foundation, which guarantees, or at least makes more reliable, the stream of interest and money, so that we know that this project it's a good candidate for applications that want to go forward in the next years. Speaking a little bit about the concepts and abstracts that Kokkos has. So the job of Kokkos is to get the intranode parallelism, either being that being on the CPU level or the GPU level, and so that one can program something that through Kokkos is ported to the different backends. And how they do that, they have a separation into kind of classes, the data structures and the parallel execution. In the data structures, there are memory spaces. So this is where the data is assigned. And depending on the backend that you want to run, there are memory spaces that are default to that backend. So you don't have to fiddle with what are the exactly memory layout that a GPU needs to work with. You can program your function, your algorithm in one way, and through the backends, they will pick the best options of the layout, whether how are the index mapped, if it is row measure, column measure, Kokkos will deal with this. And the memory layouts also have memory traits, which are bound to the memory layouts in the memory space, so that one can, for example, do an atomic write in the write backend. This is also coupled with the parallel execution, and there are different execution spaces. Mainly the examples are CPU and GPUs, but other architectures are also supported here. And each execution space has a default memory space. So if one just programs Kokkos with the default specifications, probably it will be already portable in a manner that it's much better than just writing a CPU code, for example, or writing a CUDA code. And by default, it will pick it will guess the best options, but this is a very educated guess because the Kokkos developers are working on that side, and they also work with the vendors. One can define execution patterns. So if you either want to run a parallel for, parallel reduce, or scan, and there are different execution policies. We'll go a little bit over the execution policies in the next slide. But there are ways of exposing many different levels of parallelism of the algorithm, but just passing a flag, because Kokkos is strongly typed, and through the type, it can infer what kind of behavior the programmer wants to pass to the algorithm. So just as two examples here, very commonly found in scientific codes. The first one is 1D parallel region over indexes. So in one example, if in MD codes we want to go over the whole list of particles, one can easily express the parallel region using a list from the first indexes to the last indexes. Index and passing a range policy. In this example here, the range policy is bound to the execution space, and that can be either inferred by default, or you can define the execution space related to the kind of memory layout that you have. So the defaults are really good, but you can also have a more fine-grained control if you want to. And this is passed to Kokkos as functors or lambdas. The Kokkos lambda is strict in what you can do, and it always passes values by copy, so the parallelism is guaranteed, but there is no forward guarantee, no strongly forward guarantee. So everything can run in any manner, and Kokkos will define that for you. Another example that I have here is a 3D parallel region, which is also really common to find. And in this example here, there is a MD range policy. So it's a multi-dimensional range, which goes, for example, in a 3D grid over all of the grid constituents. And this is a good example of how Kokkos works closely with the C++ standard. Actually, the Kokkos developers got the MD range in the way that they implemented in Kokkos into the C++ standard. So they have a really close relationship with the language itself, which makes this also future-proof or time-proof. So Kokkos is the intranode parallelism kind of offload, or how you want to compile your code for different architectures. And the other side of the problem that I have introduced before is due to load balancing. So if you have different workloads on different parts of your domain, one processor can slow down the whole execution of your program, and that comes naturally with different kinds of applications or with a really huge level of parallelism. And to tackle this issue here within our simulation data lab and in partnership with the MultiXscale, we developed a load balancing library that has been developed in by our group for more than 10 years as well. It has support for local and global load balancing methods, and it works both with regular grids, well, for example, orthogonal grids, cubic-shaped domain decompositions, or non-regular geometries. Focusing on the orthogonal methods, which are the ones that are more easily found or broadly implemented on scientific codes. We have implemented the tensor-based method, the staggered grid method, which are local ones, and the histogram-based method. I will speak a little bit more further down in the presentation about these methods, and all has a design philosophy that it provides a suggestion to the calling program of better balanced domain borders based on work. And work is a definition that we use to account for how much compute is being done in each domain assigned to a processor. All provides no automatic solution for communications. It provides new neighbors for each domain. So the calling program receives the new neighbors and then communicates the particles or whatever it's dealing with. Going more on the definition of work for all is a scalar parameter that describes the workload on a single domain. And that can be either the time that was spent or the number of particles. This number of particles can have weights depending on like the force fields of each particle and so on. So speaking about the integration of codes, like how all can be integrated to a software, Here on this fluxogram, things that are colored in blue are dealt with the by the calling program, and gray by the library itself. So the calling program can be anything very generic. The calling program needs to deal with the communication, the hallows, communication over boundaries. It can compute pretty much anything. It can be either particle or grid things. And one thing that's important, that's the calling program has to call the library and pass this scalar parameter, which is associated with the work dealt by each domain. And all then performs its task. It calculates better domain decomposition, so the boundaries, the Cartesian boundaries of each domain, and then passes this kind of information to the calling program along with the neighbors of that specific domain or that specific process. And talking a little bit of the applications that we have found both using Kokkos and all. So one study that we have done was to compare the performance portability of the n-body problem in different GPU through different GPU vendors. We have used different performance portability, portability programming models, and Kokkos was one of the best performing programming models. Here you see the results for NVIDIA GPUs, but we have also done this for AMD and Intel GPUs. And the performance of Kokkos is in line with the one of the CUDA native CUDA implementation. Just as a resume of the kind of results that we got through the different architectures, one can see here on the top of the table the different GPUs that we have tested. From NVIDIA, we have tested the A100 and Grace Hopper GPUs. The AMD one was the MI250, and the Intel Max GPU 1100. And if you compare the Kokkos line here with the CUDA line, sometimes Kokkos even exceeded the number of flops per second that the CUDA version could have. This is a native CUDA implementation, a shared memory CUDA implementation. And just as the take-home message of this table is that between the different programming models that we have tested, Kokkos had a really good result, as well as OpenMP to be true. Yeah. And as results of the load balancing method, this is a coupling between all and LAMMPS. On the left-hand side of the slide here, you can see the recursive bisection method. That's the native LAMMPS implementation of a load balancing. And on the right-hand side, one can see all coupling with LAMMPS using the staggered grid method. And the colors of the particles are defined by which processor owns these particles. This is a short example, very simple one, so that it's easy to understand. But you can imagine that processors 1 to 4 are being assigned to these different colors. And we have done this test. One interesting behavior is that LAMMPS native methods changes particles domain between processors, and our solution doesn't. But this, as I said, is a preliminary test just to show that these integrations have been done, and they are in a preliminary stage. Like we are still testing functionality. Another thing that all can do is to follow the system dynamics. This is very important for load balancing. In this case here, you can see like the shrinkage of one polymer, and the blue lines here define how each domain is set. And since there is a higher density in one side of the box, in one part of the box, and lower density in another part of the box, the system, through the work, calculates the new boundaries and resets and passes this information. We have done a little bit on scalability as well. We have tested this coupling between LAMMPS and all with a system of 5 million atoms using different force fields. So the EAM, which is a very light one, and the atomic cluster expansion, which generates a lot of work. Therefore, there is the necessity of load balancing in this case. We have tested this in joules machines, and one can compare, for example, the RCB time, which is the native on LAMMPS, to the staggered local, the one that I just shown to you in the previous slides. And we were able to achieve a better scalability than using the LAMMPS native method, but this is also preliminary work. So speaking of how we are coupling this with the MultiXscale efforts, first, let's have an outlook on the where we are implementing or using Kokkos and why. First, we are developing P3M Kokkos-based implementation for, and this is in close collaboration with ESPResSo, because as John Oil mentioned in the previous presentations, for the ones that were not present there, we want to have a less communication, inter-node communication, and also inter-node communication. We want to have it as slow as possible, and we are implementing this using Kokkos. So we have major rewrite of the algorithm using Kokkos for all the kernels. So everything will be able to be run either on the CPU or the GPU, depending on the architecture that you have available. You just have to compile to the right architecture and have Kokkos being installed, of course, with the right backend. We are doing FFT through Hefty. Hefty deals with the communication of the FFTs and also has different backends. So it has the QFFT backend, the ROC FFT backend, MKL, FFTW. So this solution will have many possibilities. We'll be able to run on CPU, GPU, either for general functions related to the electrostatic methods, but also for the FFT side. And ESPResSo will serve as a test application for this. So we are developing this as a library, which will be coupled to ESPResSo and tested, so we can have showcases and also contribute to ESPResSo scalability. And as I said, since this is a library solution, we will be able to make it public for the community, and other codes will be able to implement this method in a performance portable way to their solutions. And regarding the future of all, our intention is to have a better support in the integration with LAMMPS. To this stage, it is still, we are still testing the integration. We have to test for more systems and also add support for more cases, for example, triclinic domains. We have to just as I mentioned, like we are testing for speed and convergence. We want to validate our integration, having more benchmarks and comparing LAMMPS fix with the all fix for the balance method. And we want to have it in the main repository. And this can be also used for multi-level simulations, just like what it was mentioned by Tillian. The address package might be something of high interest to do some tests and to see how our load balancing solution works with. And this is kind of the connection that we have to the project. And now I think I was just looking if the Q&A would be now or not, but yeah, that is the end of my presentation. I welcome any question if you want to.